Right, let's take a 6 amp MCB as an example. So in the literature, we know that the maximum allowed ZS, so remember that's the resistance essentially of the entire fault path. We know that if that's less than 7.28 ohms, that breaker will trip in the right time, 0.4 seconds. Let's just have a look at how an MCB reacts. To cut a long story short, if we want our 6 amp breaker to trip in the right time, 0.4 seconds according to the regulations, there needs to be 30 amps flowing for that to happen. So if we just do a quick Ohms Law calculation, you can see I've done it here. So 230 volts, which is the voltage, the supply coming into your property, divided by the resistance, the maximum resistance, maximum ZS, which is 7.28, that's what it says in the book. That gives us 31.5 amps. So that means that there will be enough current flowing for that breaker to trip in 0.4 seconds in the right time. And we could do a similar calculation for every different MCB size. So we're going around and we're taking resistance measurements of every circuit to ensure that the ZS is lower than that. As long as the resistance is lower than that, then enough current will flow to trip the device. So let's just go back to our condition report. You can see that the resistance in the house, and we add that onto the measurement that we take back to the transformer, add those both together, we get 1 ohm, which you can see is much lower than 7.28 ohms, 1.06 ohms. If we do a little calculation there, 230 divided by 1.06, that gives us a fault current of 217 amps. It's more than enough to trip that breaker in the right time, 0.4 seconds. So in a report, if you hear anything relating to R1 plus R2, ZE or ZS, they're all just resistance readings that we take, and we need to make sure that those values are lower than these maximum allowed values, so that disconnection occurs in the right time, and so that the wiring of your house is safe in the event of a fault, it doesn't overheat. Now in the case of socket circuits, ring socket circuits, an old way of wiring sockets, there's an extra component to that. We need to take a resistance measurement at the consumer unit of the live, the neutral and the earth separately. So R1 is the name for line, Rn is the name for neutral, and R2 is the name for CPC or earth. And we need to make sure that they're all continuous, because if they're not continuous, then that presents a problem, because the cable could potentially be overloaded in the ring final socket circuit. So we'd need to look into that. So that's where the end-to-end resistance measurements come in, the R1, the Rn and the R2. If it's a radial circuit, i.e. it starts at the board and it just goes out to a point and it doesn't come back like it does in a ring circuit, then we don't have to do those end-to-end measurements. The next test that we do is called insulation resistance, and this allows us to assess what sort of condition the cable's in. The older the cable, the lower these values, or if the cable's been damaged in some way, these will return lower readings. So when a cable is brand new, the maximum possible value will just be, the maximum value that the meter can read. So with my mega multifunction tester, that would be greater than 999 million ohms. A fail is anything less than 1 mega ohm or 1 million ohms, and anything less than 2, we've got to look into that and investigate it further. As I said at the start, the useful lifespan of cable is generally, give or take, about 40 years. And over time, the insulation starts to break down. And sooner or later, that would result in nuisance tripping, where there starts to be, shorts or current leaking. So the insulation resistance test, you've got your 3 conductors in the cable. You've got line, neutral, and earth in the middle when you're using the domestic twin and earth cable. Now what we do is we clip onto 2 out of the 3 and we perform 3 tests between live and live, that's line and neutral, between line and earth, and between neutral and earth. And we zap it with 500 volts and we measure to see if there's any current leaking, and that returns this insulation resistance reading. So you see in each instance here, all these circuits are passed. The lights are a little bit lower, 7.46, but it's still passed. Like I said, anything less than 1 is a fail, anything less than 2, we've got to investigate it. We need to make sure that the polarity is correct. What that means is that any switching occurs in the in the line conductor only, as opposed to, say, the neutral. We've already talked about the maximum ZS. This value here is a combination of the R1, R2 plus the ZE. That's just got to be below a certain value for automatic disconnection to occur. We then come on to an RCD measurement. So the RCD is the sensitive protective device that protects you, the end user, against faults to earth. So there's 2 tests that we do. Oh no, there's a range of tests, but there's 2 things that we note down on the test sheet. First of all, we test the RCD at half its rated current to make sure that it doesn't trip, so that you don't get nuisance tripping of the RCD. And if it does, it might indicate that the RCD unit needs replacing. We then test the RCD at its rated current, which in a domestic situation is usually 30 milliamps. And when we test it at its rated current, it needs to trip in less than 300 milliseconds. And then we test it at 5 times its rated current. That's what we note down here, and the value needs to be less than 40 milliseconds. So you can see the one and only RCD unit in this board trip within 9 milliseconds, so that's passed the test. With an RCD, there's also a test button. We just simply press that to make sure that it works, and you should check that yourself. I believe the guidance is every 6 months these days. If it doesn't trip when you press the button, again, it indicates that the unit needs changing. Finally, and I personally have yet to see these in any domestic situation that I've tested, it's a relatively new protective device which has just been introduced, which I'm sure sooner or later it will be as common as an RCD unit is now. That's an arc fault detection device, and simply they have a test button, and we just need to make sure that those test buttons operate. So that's a quick overview of some of the inspections that we do, some of the things that we note down, and some of the tests that we do as well. Trying to demystify a little bit some of these numbers that you'll see on your test sheet.